Welcome back to Control System Lectures. In this video, let's talk about the sensitivity function. Now in the last video I covered gain and phase margins, and I teased you at the end with a little bit of why looking at a system's sensitivity to process variations is as important as looking at the gain and phase margin. Gain margin tells you how much pure gain increase your system can absorb before it goes unstable. And phase margin shows how much pure phase lag your system can absorb before it goes unstable. However, as I showed, in some systems, you have a combination of additional gain and phase, and then your system can go unstable much easier than you think. And this is where looking at the sensitivity function comes in handy. If you look up the sensitivity function in any control systems book, it'll display this accurate but slightly confusing equation. But once you understand the basic concept behind this equation, I think you'll find that you won't need to memorize it because it just makes a lot of sense by reasoning through it. It says that m sub s, or the nominal sensitivity peak, is equal to the maximum absolute value of the sensitivity transfer function evaluated at j omega, for omega from 0 to infinity. Now I'll come back to this equation, but let's do it from two completely different paths. The first path is using the Nyquist plot. Now if you don't have a good working understanding of the Nyquist plot, you should check out my videos on it first before continuing this video. But here are the key points. You can use the Nyquist plot to determine closed-loop stability from the open-loop system. In this case, my open-loop system is C of S times G of S, where C is the controller I'm designing and G is the plant or the process. Then you can map the open-loop transfer function from the S domain into the W domain by replacing the Laplace variable S with the Nyquist contour, and then you can plot the resulting Nyquist curve on the complex plane as you sweep around the contour from 0 to infinity, and then from minus infinity to 0. The absolute key point here is that the Nyquist plot is the plot of your open-loop system, C times G, evaluated along the Nyquist contour, which is essentially j omega, so it becomes C of j omega times G of j omega. Also, as I said in the gain and phase margin video, to have a stable system, you're really interested in avoiding this -1 point with the Nyquist curve. Gain margin tells you how much you can scale this plot before you cross the -1 point, and phase margin tells you how much you can rotate the plot by before your curve crosses the -1 point. The problem comes with a Nyquist plot that looks like this, which is very close to the -1 point, even though it has great phase and gain margin. So process variations that cause the curve to move in this direction towards -1 will reduce stability in your system. So visually we can see that we're really close to the -1 point from a Nyquist plot. But how can we tell mathematically? Well, it's pretty easy. We could just measure the distance between the curve and -1, and then just find the closest approach. This will tell us the point that is most in danger of causing instability. And distance is just the Nyquist curve minus the -1 point, or C of j omega times G of j omega plus 1. But what we really are looking for is the minimum of C times G plus 1, because that'll give us the closest distance. But we're also trying to derive sensitivity, which implies that the higher the number, the more sensitive it is to process variations. What we have here is that the smaller the number, the more sensitive. This is more like a robustness number. And that's because this number goes down as sensitivity increases, so you're a lot less robust to process variation. If we want our number to go up as sensitivity goes up, then we just need to take the reciprocal of it and then switch from minimum to maximum. And so now our equation is the maximum of the absolute value of 1 over 1 plus Cg for any part of the curve over the entire spectrum from minus infinity to plus infinity. But since Nyquist plot is mirrored about the real line, we really only need to look at frequencies between 0 and infinity. And that is exactly what the sensitivity function is. It's the minimum distance between -1 and the Nyquist curve of C of j omega times G of j omega. So the first way to think about sensitivity is just graphically on a Nyquist plot, and the sensitivity function tells us how to interpret that mathematically. But I promised two separate paths to this equation, and for the second path, we need to go to the block diagram. We go back once again to the open loop system, C of S times G of S. And if you have unity feedback, the system would look like this. And this looks like a typical block diagram for a generic feedback system. However, process variations and noise in the system can add to your output in unpredictable and unknown ways. And so we can simplify all of those various sources of error into a single input disturbance in right here before the output. Now hold up one second. I want to caution at this point that this is a simplification. These block diagram representations are just abstractions of the real system. And by lumping all disturbances into a single input at the end, I've made an assumption of how the disturbances will affect my system. This simplification is useful for teaching the theory because it allows us to focus on the fundamentals. But once you understand the concept of sensitivity from these simplified diagrams, you'll be able to apply that intuition to more complicated systems. In practice, disturbances can come from a number of places, and care must be taken to know how your mathematical model relates to the real world. Let's get back to the problem. So now our system has two inputs, in, which is the noise of the process variation, and r, which is the reference signal. And we have one output, y, for this system. And you can reduce the transfer function for the system in many ways. I just used an intermediate variable a, and then wrote it out algebraically. But however you get to the reduced transfer function, you should notice that the output y is defined by the summation of two input signals, the reference input r and how it plays through the system, and the process variations in and how they play through the system. And that's exactly what we see right here. It's a summation of two smaller transfer functions. Now let's just say for the moment that there are no process variations. Everything is perfect. And then n goes to 0 and the transfer function just becomes the normal transfer function for a closed loop system with one input, r. But if there are process variations, then the output y will be modified by the second transfer function. And notice this transfer function. It's exactly the same as the sensitivity function and is what we derived graphically earlier using the Nyquist plot. So using this transfer function, we can determine what our system's sensitivity is to process variations at all frequencies using a Bode plot. Of course, if we're just interested in the maximum sensitivity at any frequency, we get back to the nominal sensitivity peak, m of s. At this point, let's go back to MATLAB and revisit the problem we set up from the last video and see if we can use our new information to make a better system, a more robust system. And just as a reminder, our system was g of s equals this big mess of a transfer function. And the first thing I always do in MATLAB is just to create a state variable s so that it makes making transfer functions a little bit easier. And then I'll generate that transfer function g that I wrote down using the variable s. Perfect. And now we want to generate the sensitivity function for g. And we can do that using the feedback function in MATLAB. The feedback command takes the forward path, which I'll call a of s, as the first input, and the feedback path, which I'll call b of s, as the second input, and generates the closed-loop transfer function of the two. So if we want the sensitivity function, then the forward path is 1, and the feedback path is g of s, so that the closed-loop transfer function is 1 over 1 plus g of s. So let's create a transfer function called sensitivity using the feedback command. And I accidentally wrote g of s because I was following my notes a little too closely. So let's take that out and rerun it. There we go. And this is what our sensitivity function looks like for our open loop system g of s. And now we can plot this function across the entire spectrum using a Bode plot and figure out where our max sensitivity is. And it's pretty obvious. It's right here where this peak is. And if we zoom in, we can see that it's right around 11 dB. And we can convert that from decibels, and we find that it's right around 3.5. This is the nominal sensitivity peak. And recall that this system had infinite gain margin and excellent phase margin. But maximum sensitivity of around 3.5 is just way too high. Typically you want systems with maximum sensitivities between 1.3 and 2. So let's see what we can do to fix that. To start, I'm going to create 3 plots all on the same figure. The first one is just the open loop system g of s. And the second plot is going to be the sensitivity function. And then finally the third plot is just the closed loop transfer function's response to a step input. And now we'll make a few adjustments to our system and then plot on top of these plots just to see how we've done. Our first thought might just be reduce the gain of the overall open loop system. I mean, this is going to pull the gain curve down and get that peak further from the 0 dB point, which would increase phase margin for sure. And it'd probably reduce sensitivity because the region is further from being unstable. So let's see what happens if we reduce the gain by 2. If we just take g of s in all three of our previous equations and multiply it by 0.5, we'll get to see what the effect is of reducing the gain by 2. And as we guessed, the gain plot in the open loop system just dropped by 2, or 6 dB, and the phase stayed the exact same. But look at the sensitivity. It went way down, almost to 5 dB, which is about 1.7, so that's great, actually. But if you look at our step response, what we've done is we've slowed the system down, and so the rise time of our step response is a lot slower. Looks like almost twice as slow, or maybe more. And that's because reducing the gain across the entire board also reduces the gain at the very low frequencies, which affects our rise time and our step response, and our ability to follow really slow-moving reference signals. Now that might not be great, but it really depends on the system that you're designing and its requirements. Let's see if we can reduce the sensitivity of our system without affecting the low-frequency response by building a notch filter. Now I'll cover the basic of notch filtering in a different video altogether. But what a notch filter does is it tries to just affect a narrow range of frequencies centered on the center frequency, in this case 0.7 radians per second. And the Q value is kind of the width of that notch, is how wide of a frequency spectrum does it affect. So this is a Q of 2, which means that it's a pretty steep filter, and it's only really going to affect frequencies really close to that 0.7 radians per second. And to apply this notch filter, just like we did with the gain, we will multiply each g of s in all three of our equations by the filter notch. And it is very obvious in the open loop gain plot. You can see here that it really only affected the frequencies right around 0.7 radians per second. But it did some pretty funky stuff to the phase. So we can see how that affects the closed loop sensitivity in the second plot. You can see that it moved the nominal sensitivity peak to a lower frequency, but we still managed to get it right around 5 dB, which was somewhere in the 1.7, 1.8 range, which was perfect. The other thing it does for us is that it keeps our step response rise time similar to what it was with our original system, and that's because the notch filter doesn't affect the low frequency gain as much as just a straight up gain did. But there are a lot of different ways to affect your closed loop sensitivity. I showed you two, one with just gain and one with a notch filter. But it really depends on what you want your system to do, and also the complexity that you want to have when you're building up your controller. Okay, I know this was a lot to take in here at the end, and the plots are probably a little hard to see. But really the bottom line that you should take away from this is that when you're designing your system, you really need to take into account sensitivity. And how you change your system so that you're less sensitive to process variations, or so that you're more robust, will be a topic that we'll cover in multiple videos going forward as we learn to design more systems. Alright, thanks everyone for watching this video. Don't forget to subscribe to my channel so that you don't miss any future videos. And leave any questions or comments that you have in the section below, and I will do my best to answer them.